Okay, so we're just going to quickly cover electrical circuits here. The big concept that we start out with is current in electrical circuits. I is current, and it's equal to the amount of charge that passes a given point within a certain amount of time. So if 20 coulombs passes a point in 1 second, we say 20 amps is the current. So amps is the unit of current. Current's related to voltage and a concept called resistance via this thing called Ohm's law. So Ohm's law says that V is equal to IR, where R, again, this is the resistance, which measures how much a material impedes electrical flow. Okay, so for electrical circuits, Kirchhoff's laws are important. And these actually really only apply in these things called irresistible circuits. And so those will come sort of at the end of this little segment here. So suppose I have a circuit. I'm just going to draw one for kicks and giggles right here. And I have two resistors and then another resistor in parallel to the second one. So we have, let's say, 2 ohms, 3 ohms, and 4 ohms here. And let's say that I take a little trek around this loop here. Kirchhoff's laws say that my trek around that loop, that the change in voltages across all those elements, those batteries, whatever, across any closed loop has to be equal to 0, which is exactly the same as saying that if you go around a closed loop and end up where you started, you're at the same height that you started. You didn't gain or lose any elevation, so to speak. So that's the first of Kirchhoff's laws. The second is that the sum of the currents coming into a junction is equal to the sum of the currents coming out of that junction. And we frequently use this example here. If you have 3 amps, and let's say we have a branch here, and 2 amps is on the top branch, and I ask you what the amperage is on the lower branch, you would say 1 amp, because 1 amp plus 2 amps had better add up to the 3 amps that was coming into that node, and you would be absolutely right. So this is a way of saying that current is conserved. Again, these are rules that we use for irreducible circuits. Usually the strategy is to reduce the circuit and then to work upwards using 2 additional principles, which is that elements in series, we say, have the same current, and elements in parallel have the same voltage. And we'll be using that fact quite a bit, so good to keep those in mind. So what do we mean by parallel or in series? So when we're reducing a circuit, we have to be able to spot these. Series means that one element comes after the next, and that all the current going through one element goes through the next one as well. And so if I have R1, R2, and R3, like this, then we say that the equivalent resistance of those is just the summation of those three resistors, or however many are there. So this is the series here. Parallel circuits are analogous. Let's say I have, I don't know, so many in parallel here, R1, R2, and R3. Then the equivalent resistance is 1 over the sums of the reciprocals of each of the individual elements. And so it goes. So when we're talking about series, there's a couple of things to make sure that we're aware of to distinguish series from other types of, say, resistor element configurations. Let's say I have a 3 ohm resistor here and a 2 ohm resistor here. These two elements are not in series, and that's because there's a node in between them, and nodes throw off that rule. We're not guaranteed that all the current that comes through this resistor, say, will go through this one. And so the Kirchhoff's rules, the rules of series circuits wouldn't apply in that case. Analogously, not everything that looks like it's in parallel is actually in parallel. For instance, if I have 2 parallel branches of a circuit, let's say, and I have a 2 ohm resistor and a 1 ohm resistor and a 3 ohm resistor, the 2 ohm resistor and the 1 ohm resistor are not in parallel. The correct way to look at this is that the 1 ohm resistor here is in parallel with both the 2 ohm and the 3 ohm resistor. And that is extremely important to make that distinction. So it's important to reduce these two, say to consider the 2 ohm resistor and the 3 ohm resistor as a single element before we consider that element to be in parallel with the 1 ohm resistor. So there's parallel branches of circuits, and all elements on those branches are in parallel with all other elements with all other branches is the right way to think about that. So just kind of a word of caution there. So let's combine these rules really quickly and just do a quick example, and then we're going to talk about how to sort of feel your way to a solution if you're in a hurry in a problem here. I'm just going to set up a vanilla circuit here. There's 3 ohms, say. This is going to be a 2 ohm resistor, another 3 ohm resistor, and in parallel to that 2 ohm resistor, there's going to be another 2 ohm resistor there, and I'll put 14 volts here. The question is, what is the current coming through this resistor? That's the question. So what we're going to do is reduce the circuit, find the current that's coming out of the battery, and then go backwards using the rules of elements in series and elements in parallel having the same current and voltage respectively to sort of assemble what the answer to this problem is. I'm going to be careful to draw each step of this problem as well. So, it's not a dry cough. Oh, goodness me. Okay, so anyway, if we have these two elements here and they are in, these two elements here are in parallel, okay? They're on different branches of the circuit. We're starting as far from the battery as possible. So I'm going to use the equivalent resistance rule, where I have 1 over 2 ohms and 1 over 2 ohms. We're going to add those together and take the reciprocal, and the summation of that's 1 ohm. So I'm going to redraw my circuit now, and this is what it looks like now. You have 14 volts, 3 ohms, 1 ohms, and 3 ohms. You can see this problem's been a little bit premeditated. All of these now are in series, one with another. All the current flowing through one flows through the next, flows through the next, and so we can simply add all of those resistances together, and so we get a 7 ohm resistor and a 14 volt battery, and we're done with the reduction of the circuit. So the next thing that we're going to do is we're going to find the current that's going to come out of that battery there, and so we're going to use Ohm's law to do that. I is equal to V over R, so the change in voltage here is going to be 14 volts is how much we drop over that resistor, and it's a 7 ohm resistor, so 2 amps is coming out of that battery, and we're ready to move backwards now. So this resistor here isn't really here. It in fact represents a set of resistors which are in series. You can see that. And the thing which is the same for elements in series is the current. So I'm going to take the current that's coming through this resistor and I'm going to distribute it, if you like, to each of the elements inside of the circuit, inside of this step here. So notice that they're asking for the current through this element here. That element is, in fact, inside of this fake element here, which is representing two elements that are in two resistors which are in parallel with each other. So voltage is the same in that case, and I don't have that. So I'm going to use V equals IR with this resistor, and I'm going to find out that if we have 2 amps times 1 ohm, well, that's a 2 volt drop. That's what gets distributed here and here because those are in parallel. So there's 2 volts drop here and a 2 volts drop here. Now they want to know the current through this resistor. I can now find that. I is equal to V over R, where V is 2 volts, the resistance is 2 ohms, out of room. So it's 1 amp, and the problem would close itself out. So that may have been a whirlwind, and I'm going to add a little bit more whirlwindishness to this discussion right now because we're going to talk about we're going to talk. I swear this is just happening for this video. I was fine before. Okay, so let's talk about this example for just a minute here. So when we reduced the circuit, we found out that 2 amps was coming out of the battery. I could have, if I was feeling really clever and confident, gone back to the original circuit, skipping all the steps, and just come up here and drawn the true fact that 2 amps is coming out of that battery. All of the 2 amps is going to go through that 3 ohm resistor, and then there's going to be a split as it goes down either leg of the circuit that each contains a 2 ohm resistor. The question is, how will that current distribute itself? Now remember that current takes the path of least resistance, or preferentially does. And so if we have two paths that are equally resistant, we expect that the current is going to be divided equally between those two paths. So what's 2 amps divided cleanly by 2? Well, it's 1 amp that goes down either one of those. And oh my stars, that turns out to be the 1 amp that we see here. So if this seemed a little fuzzy, let's do another exercise so you can kind of see how we're working this logic here. So again, let's say that I have, I don't know, 20 amps coming down this wire. And I have a lot of elements that are in parallel with each other. And each of these is I'm making it up, 2 ohm resistors apiece. So which path will the current prefer? Well, it'll prefer them all equally well. And so the current's going to divide itself into it's going to divide itself among those 4 different paths. So what's 20 divided by 4 paths? Well, that's 5 amps apiece. You can't make this up. My grandpa used to say that you start having a hacking cough if you're lying. That's how you know if you're lying or not. So maybe I'm telling a lie. Okay, so 5 amps goes down each of those. Do you see how easy that was? So let's take another example, though. Let's say I have like 10 amps. It's coming down a circuit, and I have, I don't know, we're making it up again, 4 ohms and 1 ohm here. I ask you, where does most of the current flow? Well, current prefers the path of least resistance. Most of the current is going to come through this 1 ohm resistor because it's the path of least resistance. So not as much resistance in 1 ohms as there is in 4 ohms. Now, it turns out I can also calculate this in my head a little bit well enough. It turns out that there's going to be 4 times as much current that's going to flow through this one as this one because there's 4 times less resistance. And so it turns out that 8 amps would flow down this path and 2 amps would flow down this path. If that last calculation of me doing the proportions doesn't make sense to you, that's okay. For those of you taking a standardized test, that might be a little bit more important. But the important thing to just point out is that most of the current flows down the path of least resistance. And I will test you on that. So make sure that you know that. Okay, alright, so much for circuits, resistor circuits anyway. Let's really quickly go over RC circuits. To do that, we need to first of all talk about capacitors because that's the C in RC. So for capacitors, remember that if you have capacitors in parallel, C1, C2, C3, then the equivalent capacitance is the reciprocal rule, and so on, right? And then if you have capacitors in parallel, that's the simple addition rule. So it's kind of like the 2 rules swap places, right? So we might need to use those rules. And just like with resistors, if you're in parallel, voltage is the same. And if you're in series, we don't have current in capacitors if they've been hooked up for a long time, but we say the charge